Welcome to the notes on scientific notation. In order to watch these notes, you need to download the file and play the slideshow if it's the PowerPoint version, or to play the video if it's the MP4 version, or the video on YouTube. Obviously, make sure your speaker is on. This will go for all future notes for my instruction. Now notice, if I'm putting it in my instruction, it's something that I consider important. That means it's very likely to show up on future quizzes and on other assignments. I'm using this warm-up activity for all of my classes. Now for some of you, this might be very, very easy if you're really, really good at scientific notation. But please watch the notes anyway, because there are some things I mention that you might not be aware of, which could show up on future quizzes. If you're in the honors class, this is particularly important because eventually you are going to be writing your answers exclusively in scientific notation. We're going to phase that in, but later on, you're going to need to really, really be an expert at doing this. Okay? But it shows up in all my classes. Later on, this becomes a major thing. So please pay attention. Even if it's a review for you, bear with me. We will get to more interesting things shortly. And here we go. Scientific notation is very important to the sciences. That's why it has that name. Scientific notation is the way that we like to write numbers in science. Most people realize that it's a shorter way to write long numbers. Sometimes a really big number, like 713 trillion, you might want to write it in scientific notation. But we also write really tiny numbers, like 0.0000753. We would write that in scientific notation as well. But actually, scientific notation can be used to write any number, no matter how big or small, or just what you might call an everyday run-of-the-mill number. And it gives you a little more information about that number and how precise it is. So to write a number in scientific notation, you need to put the decimal after the first digit and then drop the zeros. Now, what is the first digit? Well, here's an example of a number that we might want to write in scientific notation. The number given there. Think about what that number is. If you wanted to say the number, how big is that number? It's pretty big. Notice that it's beyond the thousands, millions. Oh, it's in the billions. So hundreds of billions. So what is that number? 123 billion. But if I want to put it in scientific notation, I want to take the decimal from where it truly is, which is right here. Remember, there's a true location of the decimal. It's located after the number if it's not shown, okay? And we need to move it over after the first digit. So the first digit is the first thing you run into, going from left to right, moving along like we read. The first digit that isn't 0, well, that's the 1. So right after the 1, that's where I need to move the decimal. But look how far away it is from there. To move it over there, I have to multiply by tens. Every time you multiply by 10, you probably know this trick. It moves the decimal over 1. And if I multiply by 10 again, that's 2 tens. It gets to here. Multiply by 10 again, it gets to here. So that would be multiplying, let's say, by 10 to the third. 1,000 gets me, of course, to the thousandths place. So let's keep multiplying. That was 3. Well, then this would be 6. Then this would be 9. And then bloop, bloop, 2 more gets me to this number. 1.23 times 10 to the 11th power is 123 billion. It's the same number. It's got the same value. However, now that it's in scientific notation, I know more about it. Why? Because I've only kept the 1.23. That shows me that those are the numbers I have a precise measurement for. The other numbers were just placeholders. Think about it. You had to have all those zeros there in order to put the 123 in the billions place. You had to have those zeros there as placeholders. But now in scientific notation, we don't need them. And so if we don't know for sure that those are really zeros, then we just drop them. We drop the zeros. If we do know that those are truly zeros, like we've measured them precisely, well, then we could include them. You could always write 1.23000 times 10 to the 11th. It's the same value, but it has more information. It tells us how precise the number is, how good the measurement is. To make sure that you're getting this, that this is clear to you, I'm going to go through a bunch of examples. Some of them are not quite as large as the number we just saw. In fact, most of them aren't, because I think an essential thing to understand scientific notation is to see what happens when the numbers are actually normal size, not super big and not super small, just everyday numbers. So what would you call this number on the left side of the equal sign of the equation? That is 100,000, right? 100,000, well, the first number is a 1. I've got to put the decimal after that first digit. And to get it there, I have to move it a bunch of times. How many times do I need to move the decimal over to get it behind that 1? I need to move it 5 times. So you could write the number 100,000 as 1.00 times 10 to the 5th power. 1.00 times 10 to the 5th power is the same thing as 100,000. Now, keeping those zeros shows me that I know what they are, that I've measured them. If I wasn't so sure if it was just about 100,000, I could have just written 1 times 10 to the 5th power. That would show me that it's not as accurate, it's not as precise of a number that we've measured. Okay? What about the number 100? Well, this number we would not normally write in scientific notation, but let's just do it anyway. We got to move the decimal behind the 1. We have to move it over twice to get there. So what is the exponent of the 10? If we move it twice to the left, 10 to the 2nd power. So 100 is 1.00 times 10 to the 2nd power. And again, that means that I know those zeros. The fact that I'm showing them there means that I know that they're zero. They're significant figures that I've measured. If I just say 100, you don't know. Is he just saying 100 like a big number? About 100. Or is he saying 100 like I've counted them? But in scientific notation, you know that I've counted them. How about this number? Well, interesting. 600 isn't the same as 100, but it is in the same ballpark. It's in the same number of digits. Okay, it's in the same what we call order of magnitude as 100. So because of that, and because I have to move the decimal the same number of times, it will have the same exponent, 10 to the 2nd. So notice, just by seeing the 10 to the 2nd part, just by looking at the part that is off on the right, on this side, the exponential portion, that already sort of tells me about how big the number is. Is it big? Is it small? And then looking at this part, looking at the 6, that gives me more information, gives me more details. So the first thing you want to look at in a number in scientific notation is the exponent. That'll tell you, is it a big number, a small number, right off the bat. The number 10 is small enough as it is. We don't usually need to write it in scientific notation to take up less space is one reason we sometimes use it. But again, writing 10 this way tells me how precise I know that that is a 10, how good my measurement is. So if I put 1.0 times 10 to the, what power would that be? Well, I have to move the decimal 1 place, so it's going to be 10 to the 1st power. Also, if you're good at your math, you should know that any number to the 1st power remains itself, remains the same. So taking something to the 1st power isn't a function that we see very often, just because it doesn't change anything. So like 5 to the 1st power is 5, right? 10 to the 1st power is 10. And then 10 times 1 is 10 again. But now that tells me about that 0. Do I know that 0? If I didn't know it, I could write it as 1 times 10 to the 1st. That would show me that it's about 10. 75 is in the same ballpark order of magnitude as 10. So it's got the same exponent. Now notice that 7.5 times 10 to the first power takes up a lot more space than just writing 75, but it's a better way to write it, and you'll find that it actually makes multiplication and division a lot easier in many cases. If you write it in scientific notation, once you get it written in that format, it's going to make your math a lot easier from that point on. The number 1, we just write 1. But in scientific notation, what would it be? It would be 1 times 10 to the, well, we've already used the first power. It's not the first power. Do we have to move the decimal at all? No, because look, the decimal is actually already right there behind the 1, so we keep it there. So how many positions do we have to move the decimal? The answer is 0. So 1 is equal to 1 times 10 to the 0th power. Now, putting something to the 0th power is a great mathematical trick. Again, if you know your math, you probably already knew this, but some people never have seen it, so they didn't realize that taking something to the 0th power turns it into 1. So any number, no matter how big, like 500 quadrillion to the 0th power is 1. You could take any long number and do that to it. It's kind of a neat little trick. So that's where you get to 0. So what happens if the number gets smaller than that? What if the number gets less than 1? We will see on the next one. So when the number is less than 1, when it's 0 point something, well then I think you already know this. What happens to the exponent when the number is less than 1? It goes negative. Now, why does it go negative? It goes negative because what it really means when you have a negative exponent is not that it is a negative number. What it means is that the 10 is no longer in the numerator. Your 10 is now in the denominator. That may or may not make sense to you. It doesn't really matter. If it doesn't make sense to you, just remember, if the number is less than 1, like 0 point something, point anything, then you know for sure that in scientific notation, the exponent will be a negative power. So notice how many positions do I need to move the decimal here? I need to move it over 1, but in the wrong direction, let's say, to the right. So then it's going to be 1 times 10 to the negative 1 power. Okay, so what that really means is that you have 10 to the first in the denominator. So you're dividing by 10 to the first. And 10 to the first, of course, is 10. So you're dividing by 10, which is 1/10. So that may or may not make sense to you when I just say it like that. But just remember that when it's a number less than 1, it's always going to have a negative exponent in scientific notation. So what about this number? This number is even smaller. We know it needs a negative exponent because it's less than 1, correct? And how many positions do we need to move the decimal from where it begins to get after the first digit that isn't 0? Well, we have to move it, obviously, twice. So by moving it twice, it becomes 1 times 10 to the negative 2 power, negative 2 power. And that, of course, is like 1 over 100 or 1/100th. Okay, 10 to the second power is 100. If it's in the denominator, it's 1 over 100. So notice that your number becomes increasingly negative, your exponent becomes increasingly negative as the number gets smaller. So just by looking at that little exponent, you can tell that this is a small number, not super small, but it's certainly smaller than 1. And then, of course, if a number is in the same ballpark, just like with big numbers, small numbers work the same way. This is in the same order of magnitude as we just saw as 1/100th, but it's 4 times 10 to the negative 2. So just by looking at that exponent, just by looking at the 10 to the negative 2 part, you know that this is a small number. And then the 4 gives you more details. Here's an even smaller one. One thing I want to caution students against doing is merely counting the zeros. I like to count the number of positions I am moving the decimal, not the zeros, Because a lot of times, see this 0 right there above that? A lot of students don't bother writing that one. Properly, you should always write that 0. If any number is less than 1, you should never just start off with a decimal. That's bad form mathematically. You always want to put 0 point, and then in this case, 0,0,0,0,1. So if you were to just count the zeros there after the decimal, you would have only 4. But if you count the number of positions that you need to move the decimal, well, then you would see it's actually 5 positions. And that's why this is 1 times 10 to the -5 power. Now notice, if I did count the zeros and if I did write the 1 before the decimal, I would still get 5. But please don't get in the habit of doing that. Again, because many people do not write that initial 0 before the decimal, and it can confuse you. I would rather just have you count the positions you move it. Think of it, you're dividing by 10 each time you move over 1 more position. Another way that we might shorten a long number is to just give it a name. We have names, for example, for all the multiples of 1,000. These are the American ones, by the way. Not every country uses them in exactly the same way we do, so just be careful when you get into these worlds of higher economics. If you're doing a big trade, make sure to get the number written out, or in scientific notation works, but not necessarily the name, because those vary. In places like France and England, they vary from what we use. Okay, so notice that the first number I have here is 1 million, which I'm just writing as 10 to the 6th power. Well, that's 1,000 times 1,000, right? And then what's 1,000 times that? That gets us to a billion. Notice that has 9 zeros, or 9 positions behind the 1. And then we've got trillion, which has 12 zeros. Does anybody know what the next one is? You probably do. After trillion comes quadrillion. Okay, that's a number that we never used to hear about, but it's becoming increasingly common these days. Then we get to quintillion, 10 to the 18th, sextillion, 10 to the 21st, septillion, 10 to the 24th, and can you guess the next one? Think of like, what comes after September? You can probably guess it. 10 to the 27th is octillion. Okay, and then the next one is nonillion and decillion. So they sound a little bit like September, October, November, December. Not exactly, but a little bit. Anyway, that's one way to compress numbers. So we can read big numbers, and maybe that's shorter than just writing it out. Let's take one that falls into one of these categories. This number, Avogadro's number, is an incredibly important number in science, particularly in chemistry. This number we use all the time in chemistry, all the time. It's essential for counting itty-bitty little things like atoms. So Avogadro's number, well, I wrote it out there, but people don't normally write it out. Notice that I've already got it configured at the bottom for scientific notation. Notice how I've already put the decimal after that very first digit, which is a 6. After that, I've put the decimal. And then we just have to figure out what the exponent is. But before we do that, let's try to read this number. Take a minute to think about what this number would be if we were to read it. Okay, so if we were to, let's see, the first 3 would get us to 1,000. Then that would get us to million, billion, trillion, quadrillion, quintillion. What comes after that? Sextillion. So how would you read this number? If you had to read it out, it would be 602 sextillion, 214 quintillion, 199 quadrillion, which is a ridiculously huge number. People very rarely will write this number out. But think about, how many positions did I need to move the decimal to get it right there where I need it behind the 6? Well, let's see. 3, 6, 9, 12, 15, 18, 21, and then 22, 23. So the exponent is going to be the 23rd power. 6.02 times 10 to the 23rd power is what we call Avogadro's number, which is the number of atoms in a mole of something. Now notice that that's how many tens I would have needed to multiply by to get the decimal in that position. And it's nice and small. It's a much shorter way to write the number. And guess what? It's also much easier to multiply and divide that number. Now that I have it in that form, I'm going to show you it's much easier to use mathematically. 6.02 times 10 to the 23rd. Now you can tell it's a large number just because of that exponent. That big exponent tells me that is a really big number. So what if I wanted to multiply Avogadro's number by something, by another big number, another number that's in scientific notation? Well, let's take a number like this. What number is that, by the way? Imagine a 2 with 5 zeros after it. What would that be? 200,000. So what if I had 200,000 moles of something? I wonder how many atoms I would have. Well, then I would multiply these, and you might be holding your head and saying, oh, great, I got to use the distributive property. If you're pretty good at math, you might imagine that would be something that would be useful. But actually, you don't need to use the distributive property when dealing with scientific notation. And the reason is because this whole thing is just one number. This whole thing is just one number as well. It's not two separate numbers. It's just a compressed form of a single number. So when you multiply it by another number, all you have to do is, first of all, take the first portion that doesn't have the exponent and multiply it by the first portion of the other number. And then you're going to deal with the exponents. So let's see, 6.02 times 2. What would that be? That's pretty easy. 6.02 times 2 would be 12.04. So we know it's going to be 12.04 times 10 to some power. Now, how do we figure out what the power will be? Well, this exponent is 23, and notice that we're multiplying, and this exponent is 5, excuse me. So 23 and 5. What do you do with those exponents when you're multiplying again? Oh yeah, it looks just like addition. It follows the rules of addition. It's exactly like adding. It looks like adding anyway. So 23 plus 5 is 28. So now I could rewrite the product of that as 12.04 times 10 to the 28th. There's just one problem with that number. Now notice I don't have the decimal after the first digit that is not 0. So I actually need to adjust it, okay, to put it in what we call proper scientific notation. Now, by the way, that number is the correct value. It's just not the proper form. So we want to keep it in the proper form. So we got to move the decimal over once to the left. And you know that when you move a decimal to the left, that adds to the exponent. So what's it going to be now? 1.204 times 10 to the 29th, because I had to move the decimal once to the left. So notice how easy it is to multiply two really big numbers. At least one of them is really big and one of them is pretty big in scientific notation. It's a lot easier than you might expect. It makes it easy mathematically to multiply and to divide. So you multiply the first portions together and then you add the exponents whenever there's multiplication. Okay? And that's how you get your answer for multiplying numbers in scientific notation. To show an example of this, we're going to do a big calculation. We're going to calculate the number of stars in the universe. So in order to do this, we need to know, well, first of all, almost all of the stars are in galaxies. So we need to know how many galaxies there are. And we kind of know this number. We've got a ballpark figure for the number of galaxies. It's about 100 billion galaxies. Now, it's not exactly 100 billion, but it's in that ballpark. We've surveyed the universe enough to know this. So this is what we call NG, N sub G, which is the number of galaxies in the universe. And then we just need to know how many stars are in each of those galaxies. On average, if we know the number of stars in an average galaxy, then we can do our calculation. And it turns out, coincidentally, that the number of stars in your average galaxy is about the same number, in the same ballpark, 100 billion stars in each galaxy. This image is a drawing of the Milky Way galaxy. We can't really see it like this because we are inside it. Our solar system is located in the spiral arms, like there. And we can't really see it like this. But now we know that our galaxy actually has an interesting nucleus. Look here in this drawing. This is accurate, just like the one in the textbook is accurate, showing that the nucleus is shaped like a bar, not like a typical spiral galaxy that has a round nucleus. This nucleus is shaped like a bar. Think of the Milky Way candy bar. Interestingly, when they named the Milky Way candy bar, it was named after the galaxy, but at that time, they had no idea the Milky Way was a barred spiral. It's what we call a happy coincidence. So it makes it really easy to remember that the nucleus of our galaxy is a barred spiral. So 100 billion stars in each galaxy, that's n sub star. So let's see, how many zeros are there in 100 billion? If you write it out like this, you can see that there's 3, 6, 9 just to get you to the billions, and then there's 2 more to get you to the 100 billion. So what is that? How many zeros? Oh yeah, 11. So what number would that be in scientific notation? 1 times 10 to the 11th power. So when we want to multiply these numbers, which we do to get our answer, it's a little bit harder when we write them out like this. If we write out 100 billion galaxies times 100 billion stars, well, that takes up a lot of space. It won't easily fit on your calculator. You could do it on paper, take up a lot of space. Let's just write them in scientific notation. Now remember, these are ballpark numbers. So I'm not going to keep all the zeros because we just know it's about that. So I'm going to put 1 times 10 to the 11th galaxies and 1 times 10 to the 11th stars, not 0.0 because we don't know it that precisely. So 1 times 1, of course, is 1. 10 to the 11th multiplied by 10 to the 11th gives us, you add those up, what do you get? 22, right? So 1 times 10 to the 22nd stars in the universe. That is the number of stars in the universe. Isn't that interesting? And we can do that very simply with scientific notation. It's a snap. Now notice that number is actually smaller than Avogadro's number. So if we knew that number more accurately, then we might write it 1.00 times 10 to the 22nd. That is the same value. It's just implying that we would know the number a little better here. The reason I'm putting it in that form is that's the standard form in scientific notation. So let's say you're in doubt about how many numbers to keep after your decimal. Well, the default would be to keep it to the hundredths place, to keep 2 positions after the decimal. So generally, that's your best option, unless you have a very, very precisely measured number or it's just an estimate. So in this case, I would probably be better off not putting those, but I'm putting them there just to show you that that's sort of like your standard form. Now, this is Avogadro's number that we mentioned earlier. Notice that Avogadro's number is to the 23rd power. Stars in the universe was only to the 22nd power, which means that there are more atoms in a mole of something than there are stars in the universe. This would be a little more impressive if we were live and I could show you what a mole looks like, but it just gives you a sense of how small atoms must be. So anyway, you can compare numbers just by looking at the exponent. That's the first way to compare them. So remember, for numbers less than 1, it's going to be a negative exponent. That does not necessarily make the number negative. So 0.00001 is 1 times 10 to the negative 5. And then the next number, I'm not going to read it out for you, but if you notice there are 9 zeros after the decimal there, but we have to move it behind the 6. So that is 6 times 10 to the negative 10 power. Now, when you divide numbers in scientific notation, it's very similar to what we did when we multiplied. Notice we take the first portion, like the 8 there, and we divide it by the first portion, which is the 4. That gives me the 2. And then what do I do with my exponents when I'm dividing? Well, it's just like subtracting. When you're dividing them, it looks like subtraction. It follows the rules of subtraction. So the first number, the 18, minus the second number, which is the 11, what does that give me? That gives me 7. So 8 times 10 to the 18th divided by 4 times 10 to the 11th is 2 times 10 to the 7th. So notice how easy that is. If they're put in scientific notation, it becomes very, very easy to multiply or to divide. Here's a number that's kind of ridiculous. I wrote it out. People almost never write this one out. This is called the Google. Now, you've heard that word before, not usually spelled like this, right? As the search engine, as the company, Google. Now, a Google is a very large number. It was an arbitrarily chosen mathematical number. It is not a multiple of 3. Okay, it isn't 10 to the 3rd, 10 to the 6th, 10 to the 9th. It isn't one of those. So what number do you think people would just pull out of their hat if they had to pick a big number? Like kids are guessing, what's the biggest number you can come up with? Well, mathematicians do the same thing. And what they came up with was, can you guess by looking? Probably don't bother counting them, but it does add up. 10 to the 100th power. So a Google in mathematics is 1 times 10 to the 100th power. And again, that's funny because that's not a multiple of 1,000 like you would probably normally pick. They could have gone with 99, but they didn't. Okay, so why do they spell it differently for the company Google? Well, because you can't copyright a word that's in the dictionary. Well, not very easily. So what they had to do was misspell it with the same pronunciation. So the word Google implies a lot of stuff, a lot of information, a lot of data, right? So they chose it for that reason. Mathematicians didn't stop there, though. After coming up with the Google, they patted themselves on their back and they said, well, that's a pretty impressive number. But wait a second, we could use this number to construct a much larger number, a ridiculously huge number. What about the Googleplex? The Googleplex is 1 times 10 to the Google power. So at first glance, that looks like the same thing as the Google. But then when you think about it, no, to the Google power doesn't mean your exponent is 100. It means your exponent is a Google. Your exponent is 1 with 100 zeros after it, which I've actually shown here. Very, very tiny, but they're there. So a Googleplex is 1 times 10 to the Google power, which is a ridiculously large number. In fact, this number is so large, there is nothing known that we could even count with it. There's not even enough neutrinos or electrons in the universe to count with this number. So it's just one of those ridiculous numbers. It just shows you what you can easily do with scientific notation. You would have a very hard time writing out the number Googleplex. So whenever we have a number in scientific notation, well, we have usually 1 digit before the decimal, and often we have 2 digits after. So 1 digit before the decimal, only 1, and 2 digits after. Don't always have 2. Sometimes you have none. Sometimes you can have 3 or 4. It's actually unlimited how many you can keep after the decimal, depending on how precise your number is. So the smallest number you're ever going to have in scientific notation, at least for the first portion, is going to be 1.00. you're never going to have anything less than 1.00 for your first portion. And then it's going to be times 10 to some exponent. That could be anything. Okay? The largest number you're ever going to have in scientific notation for the first portion is going to be 9.99. Well, you might have 9.99999, but it's never going to get to 10. Because if it gets to 10, well, then you're going to need to move the decimal over and adjust it. So the biggest number you're ever going to have for the first portion in scientific notation is 9.99. That means it's always going to be between 1 and 10. That's why multiplying and dividing with scientific notation becomes so easy, because you're going to be multiplying and dividing by numbers between 1 and 10. And then, of course, that exponent doesn't have to be 12. That's just an arbitrarily chosen one. That could be anything. So a number that we put in scientific notation all the time is the speed of light. 3.0 times 10 to the 8th meters per second. Those are the units. Now, you're going to find that in science, we always need units. I stayed away from that in this first introduction because we just wanted to talk about the numbers on their own. But a number without a unit doesn't mean much. You'll see that very soon. So that's a number that we're going to use all the time, 3 times 10 to the 8th, 3.0 times 10 to the 8th meters per second. Another one that comes up is h, which is called Planck's constant, a very important number in science, which is 6.63 times 10 to the negative 34 joule seconds. So negative 34, does that make it a really, really big number? Remember what that means? If it's a negative exponent, what does that mean? It doesn't mean it's a negative number. It means it's a very small number. And because it's negative 34, this is an incredibly small, tiny, tiny number. But that doesn't mean it's not important, because a very tiny number can have a huge impact when it is multiplied with something. Not when it's added, then it doesn't matter. But when it's multiplied or divided, woo, it can have a huge effect. That is the end of the notes on scientific notation. Now, please do the assignment. If you have any questions, my preferred way and the way you'll get the quickest response is to message me on Schoology, and I'll try to give you as quick a response as possible.